做个 de-escalation 呢。
Hello everyone, can you hear my voice? We will start in maybe 5 minutes. Thank you. Okay, let's start. So firstly, let me try to record the video. Good afternoon, everyone. As you all know, due to current situation, we have decided that we will not have midterm exam this time. And in this case, your final marks for the advanced geotechnical design will consist of 3 parts, which are 2 assignments and final exam. So each assignment counts for 15% of your final marks, and the final exam counts for 70% of your final marks. So I hope this arrangement is okay for you. I'm Dr. Wu, and nice to meet you all. So we will go through lecture 4 and lecture 5 together in the coming weeks. If you have any questions, you can reach me by this email address. And also, if you have any question related to previous lecture, you can also send an email to Dr. Chen. And also, I want to remind you, so next week, we are supposed to have distinguished the gas from the geotechnical engineering office. We will invite engineer Professor Philip Chong to give us a lecture in next week. Okay, so let's start lecture 4. So lecture 4, we covers 2 parts, which are excavation and soil reinforcement. In this slide, you will learn different supporting methods for excavation. You will learn how to calculate the total factor of safety and how to calculate the unit factor of safety for bentonite slurry wall. And you will also learn how to calculate the lateral displacement and the settlement of excavation. And you will also learn the heave of the bottom of the cut in clay. And also, you will learn the analysis and design of reinforced earth retaining structures. Before we start introducing the first supporting method for excavation, so we need to know why we even need excavation, why we even need a supporting system for excavation. So here, let me insert one slide. So for example, if we have an excavation, so this is excavation, if the depth is smaller than 1.2 meter, for this kind of shallow excavation, we don't have to use any supporting method. It's going to be stable. But however, if we have an excavation, a deep excavation, let's say is deeper than 3 meters, the soil here is likely to collapse under its own weight. So in this case, we can either have a sloping excavation. So what is sloping excavation? It's like this. So in each side of the excavation, we will have a slope. As you have learned in lecture 3, you know how to determine the factor of safety for the slope. And then the second method is to construct a retaining wall. So this is the excavation. So we can construct a retaining wall here and the retaining wall here. So in this case, we can make sure the excavation is stable. And in some other case, you may also find we use struts, like struts to support the excavation, or we can also use soil anchors behind the excavation to support. Okay. So the first supporting method is called soldier pile wall, or in some other country like UK, it's also called king pile wall. Soldier pile wall consists of 2 basic components, which are soldier piles, absolutely, and we will also have a legging. Soldier piles are usually installed in a spacing of at 1.8 to 3 meters by pile driving equipment, or it can also be installed in a pre-excavated holes. So for driving method, we usually use bearing pile section. So what is bearing pile section? So bearing pile section refers to a steel pile which has a section of H shape or I shape. For this kind of pile, we call it bearing pile. Okay. So pre-excavated hole method is not very commonly used, but it can be used for some reasons. For example, if you want to reduce the noise or minimize the vibration, which may damage the adjacent buildings, we will try to have pre-excavated holes, and then we install the soldier pile inside the holes. And also we try to penetrate a hard layer or penetrate through borders. We prefer to use this method. And also sometimes we may want to have the pile at a precise location, or for some certain types of soldier piles, which is very difficult to drive. For these cases, we will use the pre-excavated method. Okay, so legging forms a wall between soldier piles. So let me draw soldier piles. For example, we install the soldier piles. These are the soldier piles. And between the soldier piles, usually we use legging to form a wall and also to connect each soldier piles. Okay. Soldier piles can be made of wood or steel. Sometimes can also be made by precast concrete. But in Hong Kong, so usually we use the steel sheeting as the legging. And legging can be installed in front of the phalange of a pile. So let's take an example of a bearing pile section. So this is the bearing pile section we just talked about. This part is called phalange. This is phalange. And this part is called web. So usually if we want to install soldier piles, or if we want to install a legging, we can install the legging in front of the phalange like this. This is the phalange. And we can also install the legging inside the soldier piles. Like the legging is wedged. It's wedged inside the soldier piles. So those are two methods to install the leggings. So here you can see the construction sequence for soldier pile walls. Firstly, the soldier pile is installed by this driving equipment into the soil, and then a layer of soil is removed or dig out, and then we install the first layer of legging, and then we keep digging out the soil, do the excavation, and then we install the second layer of leggings. So we repeat the same procedure, and then we finish the excavation, and also at the same time the leggings are installed. So here are some photos of soldier pile walls. Here you can see this is the bearing pile section. This is the soldier pile, and the legging is made of wood and is wedged inside the soldier pile. And here, this is the soldier pile, soldier pile, soldier pile. And then in between the soldier pile, we have legging made of precast concrete. Okay, here you can see the legging made by wood. And here we have a new structure element. It's called whale. So the function of the whale is to transfer the loading from other supporting methods such as struts or soil anchor to the soldier piles. So for example, here you can see there are something in front of the whales. So this is the top part of the soil anchors. It means behind this soldier pile, soil anchors is installed. If we look at the excavation in the other cross section, so this is the excavation, and here is the soil. And here we have the soldier pile wall. And we also use the soil anchor to tie back the soldier pile. But at this area, we prefer to use while to transfer the loading from the soil anchor to the soldier pile wall. Okay, so this is the function of wheels. Soldier pile can be used in many types of soil, except soft to medium clay and loose or soft dilatant soil, or the soil below water table. The reason of this is because the large deformation is likely to happen during the installation of the soldier pile and the leggings. Considering most of the soil in Hong Kong are sandy soil or silty soil, and high water table is found in most of the commercial areas. Therefore, soldier pile wall is not very commonly used in Hong Kong. The good things about soldier pile walls are it can achieve a fast and economical construction. It's more rigid than sheet pile wall. So for sheet pile wall, we will discuss later. And the soldier pile wall can avoid the interference with utilities easily by allowing the utilities to pass through the leggings. So what is utilities? So utilities refers to, for example, pipelines or gas lines, or sometimes even communication cables. So usually we bury these pipelines or gas line cables inside the soil. So if we need to do the excavation, sometimes we may have interference with those utilities. But as we discussed before, the installation method of the soldier pile is we install the soldier pile first, and then we install the legging. So for example, if here we have a pipeline here, so for this level, we can just relocate the legging from this level to this level. So we will make sure at this level, we will not have legging to stop the utilities. So by this kind of relocation, we can avoid interference with the utilities. However, the soldier pile is applicable only for self-standing soil, and ground loose can happen during the installation of leggings, and it cannot achieve a watertight wall. This is very important for excavation, because if we don't have a watertight wall, if there's a underground water flow, so it's very dangerous for the excavation, especially at the bottom of the excavation. So we will talk about this later. And also this method cannot act as a permanent wall. Okay. The second supporting method is called steel sheet pile wall. This method is very commonly used in Hong Kong because it's very effective in cutting off the underground flow. Okay, so usually shoring or later support system such as struts or soil anchors are also used together with sheet pile with the interval of 2 to 3 meters. The advantages of sheet pile walls are this method is relatively economical and good for controlling the underground water and can be used for unstable soil. And this method can be used for very deep excavation if proper strut is installed. And can also achieve a fast construction. Similar to soldier pile walls, this method will generate noise and vibration, which can affect the adjacent structure and utilities. This method is not that easy to pass through hard layer, and also it cannot pass through the border easily. And this method cannot avoid interference with utilities. This is not like a soldier pile walls, because in soldier pile walls, we can relocate the legging, but sheet pile walls, this is impossible. If we have utilities under the sheet pile walls, we may consider to remove the sheet pile wall and then change the location of the sheet pile wall. The sheet pile wall itself is a flexible retaining wall, and therefore the ground improvement can be very significant. Okay, and this method requires a certain headroom. So you can see here, this is the equipment to install the sheet pile wall. So we need to have a certain area for the equipment to operate. And also similar to soldier pile wall, usually the sheet pile wall cannot act as permanent wall. Okay. So here you can see the construction sequence of sheet pile wall. Sheet pile walls are formed by interlocking. So you can see interlocking the sheet pile section. So we install the sheet pile section by section. After we finish the installation of the sheet pile wall, and then we start to do the excavation. This is different from soldier pile wall. Here we have two typical types of the sheet pile wall section. The first one is like this section, but sometimes you may also see it in this way. So this is one section of sheet pile wall, and this is the another section, and then the connection is at this location. So this kind of section, we have a name for it. It's called Larsen section. And the second section type, we can see the connection location is different. The first one, the connection location is at this area, but the second one, the connection is at here or here. So this one, we call it Vortigern section. This is called Vortigern section. Okay. As we discussed before, this method is very good at cutting off the water flow. So it can be used on the sea side. For example, this one, this is sea. This is sea water. It's very good at cutting off the water. So the water, it's not easy for the water to penetrate inside. So this method is also very useful to form a cover dam. So you can consider this one is a cover dam. Okay. And here you can see this is the steel pile, and then here we have whales, and we have struts, and corner struts. Okay. The third method is called board pile, or it can be also called piled wall. So this method, usually it constructed together with, it worked together with soil anchors or soil nails. And sometimes you may also see it with the struts together. You can see this is the strut, and this one is whale, we just talked about, and this is also struts. This one is the board pile, and here we can also see the board pile, and also in front of pile we have soil anchors, this is soil nail. Sorry, this is soil nail. And here we have soil anchors. So I think you already know the difference between soil nails and soil anchors in lecture 3. So for soil nails, it won't have a tension unless the slopes start to move. But for the soil anchors, we apply pre-tension to the anchors. So this is the main difference between soil nails and soil anchors. Okay. This slide shows the construction sequence of bored pile. So first of all, a borehole is formed by using this kind of equipment. It's called auger. Okay, so this is a borehole, this one. So that's why this method is called bored pile, because first of all, we need to have a borehole. Okay, and after that, we install a rebar cage. This is the rebar cage. And then we do the concreting to form a pile. So one pile is complete. And then we repeat the same procedure. We can form an entire wall. So for the bored pile, we can have different cross section. For example, this one, we can consider it as a tangent bored pile wall, which means each pile, they are tangent to each other. But of course, you can also have a certain small spacing between each pile. But however, this section is not as good as this section because the water may flow in between of the bored piles. And sometimes you may also find a section which the pile, they are secant to each other, like this. So for this kind of section, actually, we call this pile primary pile, which means we will install this pile first. So for this pile, it's not necessary to have a rebar cage. So sometimes we can just mix the soil with cement or lime to form a column. And later we do the borehole here, 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 and here. So this pile, we call it secondary pile. So for the secondary pile, it's required to put rebar cage inside and do the concreting. Okay, so here we have a like typical section for bored pile. So the next supporting method is called diaphragm wall. So this method relies on reinforced concrete retaining wall, which allows a very deep excavation, and the diaphragm wall itself can serve as a permanent structure element. And also diaphragm wall, compared to the supporting method we discussed before, diaphragm wall can also support a high vertical loading. Okay. The typical construction process of diaphragm wall can be summarized as follows. So firstly, we need to construct a guide wall. And then we do the excavation to form a panel. And then we fill the panel with spentalized slurry. We install the rebar cage and do the concreting. And then we connect each two panels to form an entire wall. So here you can see the construction sequence of how to construct a diaphragm wall. So firstly, we need to construct a guide wall. A guide wall is constructed to set out the position for the retaining for the diaphragm wall. So the guide wall is usually with a depth around 1.2 meter and the width around 0.8 to 1 meter. So it's written here. And after we forming a guide wall, so we use the grab cutter to remove the soil to form a panel. So we form a panel, and the excavation is stabilized by filling it with bentonite slurry to support the wall of the excavation. So after that, we install the rebar cage, and then we cast the concrete wall. So like this, and then we finish one panel of the diaphragm wall. By repeating the same procedure, the entire wall can be constructed. Okay. So diaphragm wall is second most commonly used supporting system in Hong Kong because the depth of the basement required in Hong Kong. Okay. Diaphragm wall can be used for unfavorable soil or unfavorable hydrological condition. It can control the groundwater during the construction very well. And this method will generate less noise and less vibration. And this method is applicable for very great depths. So most importantly, this method can act as a permanent wall. Compared to the previous supporting method, diaphragm wall is kind of rigid wall. So if we have a diaphragm wall, the settlement due to the excavation is gonna be minimal. And as we just discussed, the diaphragm wall is kind of rigid wall, so we don't need to use so many struts. So for example, this is the excavation. If we have a sheet pile wall, we may need several layers of struts. But if we have the struts, this whole area is gonna be blocked. So we cannot use this area for other construction unless we remove the struts. But for retaining wall, but for diaphragm wall, because it's a rigid wall, so we may not necessarily to use the struts or the additional supporting method. So this whole area we can use for other construction. Okay. However, site congestion may happen, as we discussed before. The construction of diaphragm wall actually is not easy, it's quite complicated. We need to use different machines. So first of all, for the guide wall, we need to have a cutter to form this kind of guide wall. And after that, we need to have a grab cutter to form the panel. And we also need to think about where to put the rebar cage or where to form the rebar cage. And also we need to have a station to mix the concrete. And also here, we need things we need to use the bentonite slurry. We also need to think about where to put the bentonite slurry before and after the construction. So that's why for this kind of supporting method, we may have site congestion. And also this method is very expensive compared to other supporting methods. Also, the disposal of bentonite slurry can block drainage easily and cause a pollution around the site. And similar to sheet pile wall, this method cannot avoid the interference with the utilities. Okay. So here, let's talk about bentonite slurry. So bentonite slurry, we can also call it engineering slurry. So bentonite slurry or engineering slurry is formed by mixing the bentonite with water. Bentonite is a naturally occurring clay, which means it already exists naturally. It's not man-made. And for this kind of soil, it contains the mineral of montmorillonite. So this is a special mineral which can form a thixotropic slurry when added to water. So what is thixotropic slurry? Thixotropic means if the soil is mixed with water and it behaves like a gel, if there's no disturbed, if it's not disturbed or under static condition. However, if we disturb the soil, or if the soil is under dynamic condition, so this kind of soil will become like a fluid. So for this kind of properties, we call it thixotropic. As you can see in this figure, if we pump the bentonite slurry, it's actually like liquid or water. But if the slurry is settled down in the, for example, the cylinder is under a static condition, it behaves like gel. And also bentonite, so for this kind of soil, its permeability is quite low. It's extremely low compared to other types of soil, especially like sand or silty soil. And also, the bentonite slurry has a similar density to water, or marginally higher than the water. You can see here. So if we use different dosage, actually we can adjust the unit weight of bentonite slurry. So for supporting the stiff clay, so usually we just use 4% of bentonite by the weight. And then in this case, we can reach a unit weight of 10.2. And if we use bentonite slurry inside the excavation of coarse sand, for this case, we prefer to use a little bit more bentonite, like 10%, and we can reach a unit weight of 10.6. Okay. So here again, we show we use the bentonite slurry to maintain the stability inside excavation panel. And here we have a so-called stop and tube before we do the concreting. So the stop and tube is to prevent the direct contact between the concrete and soil. So we don't want the concrete to directly contact with soil, especially at the early stage. So this is why we install this kind of stop and tube during the construction. As we talked about before, so the bentonite may block the drainage, or it may also cause, have some pollution problem to the surrounding area. So therefore, we prefer to reuse the bentonite slurry. We call it, here we have a recirculation of bentonite slurry. So here we have a excavation panel. So before we do the concreting, the panel is filled with bentonite slurry. And after we do the concreting, as we discussed before, the bentonite slurry, the unit weight or the density is similar to water. So the bentonite slurry is gonna flow on top of the concrete, and And then if we keep casting the concrete, the bentalized slurry will be pushed up. We're going to be pushed into the pipe and be transferred all the way to a stabilization storage tank. So also due to the light density of bentonite, so it's not difficult to separate the bentonite with other soil particles. So in this case, we use the bentonite. So the lower part's gonna be, for example, sand or other soil, which is heavier than bentonite. And then we take this used bentonite and we mix it with water, and then we can form a new bentonite slurry. And then we pump this new bentonite slurry to a newly excavated panel. And then after we finish the concreting, we can reuse the bentonite slurry again by guiding it into this stabilization storage. In this way, we can achieve the recirculation of bentonite slurry. Okay. So in this slide, you can find a typical height of the commonly used retaining wall for excavation. Here you can see sheet pile wall. You can see the soldier pile wall. And for this continuous pile or this secant pile, those are all board pile or pile wall. Also, we have a diaphragm wall here. So in this table, you can see, for example, if we don't have, we have a cantilever, which means we don't use any other supporting method. We just build the wall. So here you can see, and for the diaphragm wall, so it can reach like 50-meter depth deep. Okay. So here are some photos. You can recognize this is our block set. This actually looks a little bit different from what we have it now. And this is the photo taken during the construction period. And then you can see when we do the excavation, we use the sheet pile wall. This is sheet pile wall. And also we have the struts. You can see so many structures used. So this area is blocked because of the strut. And here are some photos of the central bypass next to the IFC Tower 2. As you can see, okay, I see one question. Why the soil does not collapse after the bentonite slurry is added to the excavated ground? Okay, this is a very good question. And actually we will discuss about this later. So now you can see we have a design for bentonite slurry wall. So I will answer you the question here, okay? Okay, let's go back to this slide. You can see this is the sheet pile, oh, sorry. This is the sheet pile wall. This is sheet pile wall. As we discussed before, sheet pile wall is very commonly used in Hong Kong. Okay, so now let's move to the design of the bentonite slurry wall. Okay, so right now I can answer your question. So here is the excavation. So inside excavation, we actually fill it with bentonite slurry. As we discussed before, the bentonite slurry is a 6 tropic slurry. So if we fill it inside the excavation, and then so right now it's on the static condition, which means this bentalized slurry will behave like gel. So what is gel? You can also see maybe like tofu. So when we have a bentalized slurry here, so we have a pressure distribution of the bentonite. This one. This is the so the distribution which the sigma bentalized slurry is equal to the unit weight of the bentalized slurry times the depth. So here we can also calculate the resultant force of the bentalized slurry. So we use F slurry to represent the resultant force. As you can see, this force will prevent the soil to collapse inside the slurry, inside the excavation. Okay. Let's say if we don't use the bentalized slurry, if we just leave the excavation like this, if we don't have the bentalized slurry, so on the other side of the excavation, we have water pressure. So here is the water table. It's above the excavation line by m times z. Okay, so we can easily draw the water distribution. So the water pressure here equals to the unit weight of water times the depth. And then we can also calculate the resultant force of the water. And similarly, we can calculate the earth pressure distribution behind the excavation. So if we don't have the bentalized slurry, so these two forces will let the soil have a inward movement. In this case, it's gonna collapse. But if we have the bentalized slurry, there's a resistance to prevent the inward movement. So let's say if this load or the pressure provided by the bentalized slurry is high enough, more than this and this, so this excavation is very stable. So maybe the soil's gonna be compressed in this direction. Okay, so that's why the I think this one can answer your question why the soil does not collapse after bentalized slurry is added into the excavation. Okay. Okay, so the philosophy of design the bentalized slurry is to find the is to calculate the factor of safety, which is defined by okay, here we have two types of factor of safety. We consider the total factor of safety and unit factor of safety. So as you can see, the total factor of safety is defined by the force, the resultant force here. Okay. And the unit factor of safety is defined by the stress. Let's go back to the previous slides. So as we just discussed before, so inside the excavation, we have the pressure provided by the bentalized slurry, which is the resistant to the collapse of the excavation. So this one is the resistant. And we also have the soil pressure, earth pressure, and the water pressure, which will cause the collapse of the excavation. So therefore, we define the factor of safety equals to the F slurry minus F water divided by the F soil. And here you can see we use F soil 2D, and here we have F soil 3D. And why we have the 2D and 3D? So, okay, so right now I will explain this. So for the excavation, it's actually in a 3D case, which means the direction perpendicular to this surface. This one, let's say maybe we use D to represent the length of the excavation. So this one is not infinite. So for the slope analysis, you have learned in lecture 3, we have assumption that the length in this direction is infinite. So in that case, we can consider the slope is on the 2D plane strain condition. So in this condition, we can take the unit length. So we can consider this one equal to 1 and to do the analysis. But however, for the excavation problem, this one cannot be treated as plane strain condition. It's actually a 3D situation. So that's why we distinguish the soil 3D, the F soil 3D or sigma soil 3D. But here is for simplification, we convert the 3D condition into 2D condition by consider a factor A. Okay, so A can be calculated by using this equation. So here we have N. N is equal to the depth Z divided by the panel length L is here. And for this equation, we also require to know the active earth pressure coefficient, which is Ka, and also we need to know the friction angle phi. Okay. So for the 2D case, we can calculate the soil pressure, the horizontal soil pressure by using the active earth pressure coefficient Ka to multiply the vertical stress, and then we get the horizontal stress. So we get horizontal stress. We get horizontal soil stress 2D. Because this one, horizontal soil stress 2D, is under a 2D condition, so we need to transfer it back to a 3D condition by multiplying the factor A. Yeah, by multiplying the factor A, and then we get the soil in 3D condition and the resultant force in 3D condition. So, okay, here we have an example. So let's assume the soil is uniform soil. And then we have water and slurry at the surface of the excavation. So first of all, let's calculate the pressure inside the excavation provided by the bentonite slurry. First of all, we can draw a pressure distribution. So this one is sigma slurry, which equals to the unit weight of the bentonite slurry times the depth. And outside the excavation, we can have we can calculate the water pressure distribution. which equals to the unit weight of water times the depth. Okay, and then we calculate the horizontal, because this is below the water table, so we use effective stress to calculate the earth pressure distribution. So for the sigma soil 2D, we can use this equation. So we have active earth pressure, Ka, and the effective vertical stress equals to the gamma soil times the depth. And then we can calculate the factor A. So here we use the unit factor of safety. So here we know the sigma slurry, and then we know the sigma water. We have the factor A here, and then we have the sigma prime soil 2D. And then we do the rearrangement, and then we can have this equation. Okay, so right now let's consider what happens if the depth Z approaches infinity. So let's see, here we have the depth and depth here. So for this term, if Z approach infinity, this whole term approaches to minus infinity. So for the exponential function curve, the curve is like this. So if this term is minus infinity, it means this function is approaching to 0. So this term disappeared. And then we have this equation. And right now we have another depth here. If this depth turns to infinity, the factor of safety turns to infinity. Means at this level, the excavation is extremely safe. Okay, so right now, for example, if we take a shallow depth, let's say like 20 meter, and then we use the same equation just here, we let Z equal to 20, and then we can calculate the factor of safety equals to 0.639, which is smaller than 1. Okay, so right now we have another question. So I see why only soil need to consider 3D, but water doesn't need to consider 3D. Okay, so this is also a very good question. So the main problems is, let me erase this content. So this is actually because the difference between water pressure and soil pressure, okay? So for water pressure, it's the same at every direction. So for example, if we have let's say a excavation and then we have water inside here. So the water pressure, it only changes with the depth. So towards this direction, the water pressure equals to the gamma water times the depth. And this direction, the water pressure also equals to the gamma W, gamma water, which is the unit weight of the water times the depth. And also in this direction, this direction, this direction, if the depth doesn't change, it all equals to gamma W times the depth. This is for soil, for water, but let's see for soil. So for soil, we distinguish the vertical stress and horizontal stress, right? So for this one, So we can have a relationship between the vertical stress and horizontal stress. So we assume the horizontal stress equals to coefficient, earth pressure coefficient times the vertical stress. The tricky part is how to select the value for the coefficient K. So I'm not sure whether you still remember what is Ka, Kp, and K0. Okay, so let's review this. So Ka is called active earth pressure coefficient, and Kp is called passive earth pressure coefficient, and K0 means the earth pressure coefficient at rest. So these three values are different. So for example, if we consider it in 2D plane strain condition, if there's no movement of this part of the soil, so we prefer to use K0 to calculate the horizontal stress. However, if for a 3D case, it may have a deflection in the direction perpendicular to this surface, which means the soil at this point is no longer at rest condition. So in this case, we cannot use the K0 to calculate the sigma horizontal. In this case, we may need to use Ka or Kp. So this is the main difference between the earth pressure and water pressure. So even we consider water pressure in 3D, as we discussed before, the water pressure in all the direction is the same. It's equal to gamma water times Z. So that's why we don't need to consider the 2D or 3D case for water pressure. So I hope this one can answer your question. So if you have any other question, you can also let me know or send me an email. So right now, let's have a maybe 8-minute break, and then we will come back at 5:40 p.m. Okay. Okay, let's continue. First, let me resume the recording. Okay, so here we have another question. Is it also common to use board pile wall with soil nails for excavation work in Hong Kong? Okay, this is also a very good question. Okay. So the answer is actually not very common to use the board pile with soil nail together, but we do have like few cases. The main reason is, for example, let me draw a cross section of the excavation. So this is the excavation. We have the board pile. And then if we install the soil nails or soil anchors, it's gonna penetrate into the soil behind the board pile wall. Okay, so this one is actually okay if there's no other structure behind the board pile. For example, here you can see there's no structure here, so we can install soil nails inside the soil. But however, we can see this figure just behind the retaining wall. We have buildings, and also it has like 1, 2, 3, 4, 5 floor buildings. And maybe behind this building, we may have like taller buildings. So it means for this kind of building, we may have a foundation. We may have a foundation, let's say pile foundation. So if we have a pile foundation here, usually we don't use soil anchor or soil nails anymore because the installation of the soil nail is going to damage the pile foundation of the adjacent building. And also, as we know in Hong Kong, we don't have enough space. So that's why it's highly unlikely to find a place to do excavation without surrounding buildings. So usually we don't use the board pile wall with soil nails for excavation. So in case the strut is very common. It's very commonly used in Hong Kong because it will only take the space inside the excavation. It will not take any space outside excavation. So it will not have interference with the structure outside the excavation. Okay, so I hope this one can understand your question. Okay, let's continue. We have already discussed the design of ventilized slurry wall, and here we have an example which we will discuss in next week's tutorial. And here, let's move to the next section, so which is about lateral displacement and the settlement of excavation. Okay, before we discuss about the settlement calculation, let's look at strutted excavation. So which means for this excavation, we will not only have a retaining wall like sheet pile wall, we will also have struts. Okay, here, for example, we have excavation supported by sheet pile wall and struts. So we have like 1, 2, 3, 4 layers of struts. The construction sequence is that we do the excavation for the first layer of soil, and then we install the first layer of struts. And then we do the excavation for the second layer, and then we install the second layer of struts. And also we have another layer of excavation, and then we install another layer of struct. This is also, or we remove the next layer of soil, and then we install another layer of struct. Okay, so this is the construction sequence for the struct excavation. So consider the sheet pile wall is kind of flexible. It's a flexible retaining wall. We have already discussed about it. So it will have a lateral deflection, even though we have a supporting system like struct. And due to this deflection, the earth pressure behind the sheet pile wall, the distribution of the sheet pile wall becomes very complicated. Okay, so right now let's just take a simple example. If we have an excavation here, then we have a retaining wall, for example, sheet pile wall here. Let's say we have only one layer of struct here, okay? So if the retaining wall is stiff enough, so it will not have any movement, and the earth pressure behind the retaining wall is going to be K0 times the vertical stress. The K0 is the earth pressure coefficient at rest, okay, which is the coefficient corresponding to the case that there is no movement of the retaining wall. So there's no movement of the retaining wall. The earth pressure distribution is like this. However, due to the support of the struct and also the earth pressure behind the retaining wall will have a rotation about this point. And due to this rotation, it will have a deformation at the bottom of the excavation. And due to this deflection, the soil at the lower part of the excavation is no longer at a rest condition. So it will become an active condition, which means the soil is compressed vertically. So in this case, the soil is going to be Ka times the horizontal stress. As we know, Ka is smaller than K0. So in this case, due to the deflection of the retaining wall, so the pressure distribution actually changed. So to be specifically, due to this deflection, the earth pressure decreased. So you can see this is another figure to show you. So in the lower part of the retaining wall, the soil is at a rest condition. So we have K0 2 times the vertical stress, but the lower part of the soil, due to the deflection, so we have a active condition for the soil. Okay. So for this kind of pressure distribution changed with the deflection of the retaining wall, this effect, we call it soil arching. So right now you can know if we consider the stress and the deflection of the retaining wall, the earth pressure behind the retaining wall is going to be very complicated. So right now we just talk about one struct. But what happens if we have so many layers of struct? For example, this one. So for this case, the earth pressure distribution is going to be more difficult than this case. And for this situation, we will change our strategy. So for this kind of situation, so we will focus on the horizontal force or horizontal load taken by the struct. Okay, so this one we can actually measure it. For example, if we put the load cell here, load cell or transducer here, for example, strain gauge, if we know the Young's modulus and the cross section, and then we can calculate the force. So in this way, for example, we measure the force. Let's say this one is equal to 50 kilonewton, and this one equal to 80 kilonewton, and this one equal to, let's say, 100 kilonewton. And this one, let's say maybe 70 kilonewton. Okay, so this load is actually measured from the transducer. So after we get this horizontal load, how do we determine the pressure, earth pressure behind the retaining wall? So here we do a simplification. So for example, here we cut the retaining wall from here, and then we have a section. This is the section. And then we assume the earth pressure behind the retaining wall is evenly distributed. So this earth pressure, we can calculate it by the horizontal load divided by the area of this section. So this one, F1, is 50 kilonewton. And also similar here, we can have a section here, and then the horizontal earth pressure 2 here, we can calculate by 80 kilonewton divided by the area of this section. And then here, we can have the horizontal earth pressure equals to 100 kilonewton pressure diagram for the structed excavation. However, it should be noticed that the pressure distribution given by the empirical method is not the real earth pressure distribution. In fact, so this, for example, this pressure diagram is actually an envelope for safety consideration. Okay, let's go back. So here we have pressure distribution behind the retaining wall. This is due to we have the measured load. But for example, if this one changed from 50 kilonewton, let's say, to 100 kilonewton, and the distribution of the pressure is going to be larger. So here for the design, actually, we choose an envelope. So inside this envelope, we consider all different kinds of combination of the loading, and then we need to make sure. So we have such envelope that covers all the situation. So here we get the empirical pressure diagram for the stratigraphic excavation. Here we distinguish sandy soil, sand or clay. For sand, the apparent pressure diagram is in a rectangular shape with the maximum intensity equals to this value. And for sand, the active earth pressure coefficient equals to 1 minus sine friction angle divided by 1 plus sine friction angle. And for clay, we introduce a so-called stability number N, which is the vertical stress gamma H divided by the unjoined shear strength, Cn. As we can see, for the soil with higher Cu, then we will get a lower N value. Okay, so for the soil with the stability number smaller than 4, we consider this clay as a stiff clay. And for the stiff clay, the apparent pressure diagram, we consider it as in the shape of a trapezoidal shape. And the maximum intensity equals to N times gamma H. And for N, usually we choose N equals to 0.4. But for a short construction period, we choose N equals to 0.2. And if the soil with the stability number N larger than 6, we consider it as a soft clay. Okay, so the apparent pressure diagram is a shape of a right trapezoidal shape. So this angle is 90 degrees. Okay, so the maximum intensity equals to 0.1 times the active earth pressure coefficient times the gamma and times the H. And for the active earth pressure coefficient, is different from what we have for sand. So for clay, for normally consolidated clay, we have the equation for Ka. So we choose M equal to 0.4. But for over-consolidated clay, so we choose M, this value, equals to 1. Okay, so if we have a clay with the stability number between 4 and 6, so actually for this case, we will consider either this situation and this situation, and then we will calculate which one is bigger. So for example, if this one is bigger, we use this value to do the design. And if this one is bigger, we use this value to do the design. Okay. So now let's talk about the prediction of ground settlement. Here we will introduce 3 calculation methods. The first method is an empirical method based on a design chart. So the design chart was proposed by a scholar. His name is Peck. Okay, so Peck, he proposed this method based on the data obtained from the previous excavation supported by soldier piles and sheet pile walls with struts in the similar soil condition, which means this method is actually suitable for the excavation supported by soldier pile and sheet pile wall with struts. So for other type of excavation, for example, board pile or diaphragm wall, this method may be not suitable. Okay, let's go through this method. So for this method, we have like a design chart here. So here we have the distance from the excavation X, and it's normalized by the maximum depth of the excavation. So here we have excavation. So this one is the maximum depth of the excavation. And then the distance is from the edge of the excavation here. So this one is X, okay? And then here we have the settlement normalized by the maximum depth of excavation, delta H over D, okay? So this method, we distinguish the soil condition and the construction of the supporting method. So as you can see here, we have 3 zones, which are A, B, and C. So for zone A, which refers to sand and soft clay, and then and we have average workmanship for the soldier pile and the sheet pile wall. And for zone B, is for very soft or soft clay and limited depths below the base of excavation. And we have zone C, is very soft or soft clay and the great depths below the base of excavation. As we can see, so A is for sand or soft soil, and B is for very soft, B and C is for very soft soil. So the settlement in type B and type C soil is going to be bigger than the settlement in type A. Okay, let's see an example. So for example, excavation with the maximum depth D equals to 15. So the D equals to 15 meters. And we consider a type A soil. So for the type A soil, let's calculate the settlement at the edge of the excavation, which is this point. So this point, we have X equals to 0. And then X divided by D equals to 0, which means we have the point here. And then from this curve, we can see the settlement over the depth of excavation, delta H divided by D equals to 1%. We already know D equals to 15. So we can calculate the settlement delta H equals to 0.1 meter at the edge of the excavation. Okay, so then let's look at X over D equals to 2, which means the distance from the excavation is 30 meters. So it's this point. So for this point, we can see the delta H over D is nearly 0. So we can conclude that at this point, there's no ground settlement. Okay, so now let's look at the X over D is equal to 1. So it refers to this point. So for this point, we can get the delta H over D is around 0.3%. And we know D equals to 15 meters. And then by using this design chart method, we can calculate the settlement is around 0.05 meters at this location. Okay, so in this slide, we will introduce a second settlement calculation method. So this method is also an empirical method. As we can see in this method, so firstly, we can determine the settlement at edge of the excavation, which is S0. So we calculate S0 by using this equation, R0 times H. H is the excavation depth, and R0 is the settlement ratio, which we can determine from this design chart. So we can see here, the settlement ratio R0 is related to the drive density dr. For example, here, if we have the dr equal to 0.8, so we can find the R0 is maybe around 0.8. And then from this chart, we can also find the friction angle. So if we have dr equal to 0.8, it refers to a dense sand. And for this dense sand, we can have the friction angle. We estimate the friction angle phi equals to 35 degrees. Okay. So you should be notice that this method is only for sandy soil. It's not suitable for clay. So this one you need to pay attention. And it is assumed that the ground settlement will only occur within a zone with the distance equals to b. So this is the zone in which the ground settlement will happen. Okay. So the distance b can be calculated by this equation. From here, we need to know the depth of the excavation h, and also we need to know the friction angle, which we can get from this table. Okay. And after we get the settlement at edge of the excavation and the settlement, the distance of the settlement, and then we assume the ground settlement curve is calculated by this equation. And for this equation, S0 we already know, and B we just calculated, and for the X. So this X is different from the previous method. You can see the previous method, the X is calculated from the edge of the excavation to the right side. But for the second method, you can see the X, the 0 point of the X is selected at this point where there's no settlement and it's towards to the left side. Okay, so this you need to pay attention to. And then here we have two factors, which are F1 and F2. F1 is the factor related to the workmanship. So for the workmanship of the retaining wall or a supporting method, we can have excellent workmanship, good workmanship, average workmanship, or poor workmanship. As we can see, if we have excellent workmanship, the F1 value is smaller than 1, which means it will have a less settlement. If we have a poor workmanship, the value of F1 is equal to 1.1, which will increase the settlement. Similarly, for the factor F2, this refers to the construction difficulties. So this means how difficult to do the excavation. If it's not difficult at all, so we have F2 equals to 1. If it's average, we have F2 equal to 1.02. But if it's very difficult to do the excavation, and then we have F2 equals to 1.05. Okay. And here we have another example. So this example, we will go through it in next week's tutorial. Okay. So here we have the third method for settlement calculation. So this method is a semi-empirical method. So in this method, first of all, we need to estimate the lateral wall deflection profile. So usually this is done by numerical analysis, or for example, finite element software. Okay, so let me draw excavation first here. This is the excavation. Then we have a retaining wall. Okay, so the first step is to estimate the lateral wall deflection. So let's say if we already know the lateral deflection of the retaining wall, okay, and the next step is to calculate the deflection volume, is the volume of this area, Vs. Okay, so for calculating the volume Vs, we also use a numerical method, or we can use trapezoidal formula or Simpson 1/3 rules. Okay, and here we have a assumption, which is the deformation, the deflection volume Vs equal to the volume of the settlement volume. So the volume or the area of this area equals to this area. Okay. So in next step, we need to estimate the lateral distance of the settlement. So here we have the settlement area. So we need to determine how big is the area where the settlement is going to happen. So this is D. Okay. So for determining D, for clay, we used Caspe method, the method proposed by Caspe. Okay. So inside the Caspe method, firstly, we need to determine the wall height to the dredged line, HW. So this one is actually equals to the depth of the excavation. This one is HW. And then we need to calculate a distance below the dredged line. This one is called the dredged line or cut line. Okay. So we need to determine the distance of this part. So this part, we call it HP, okay? So if the clay, we don't consider friction angle of the clay, then this depth, this distance HP equals to B. B is the width of the excavation. This is B. Okay, so this is for the case that we don't consider the friction angle of the clay. Okay, the second case is we consider both the friction angle and the cohesion. And in this case, we use this formula to calculate HP. And then we calculate another factor, HT, which is equal to HW plus HP, which is the distance from the surface of the excavation to this point. This one is HT, okay? And then for the Capse method, we can calculate the lateral settlement, we can calculate the distance D by using HT. Okay, here is the equation for determining the distance D. Okay, so HT here, HT equals to HW plus HP. So this one is HT. So by using this equation, we can determine the distance. And as we just mentioned before, we have assumption that the deflection volume, this one, deflection volume, is equal to the settlement volume, this one. And then we know the distance is D. So we have the deformation volume Vs equals to the settlement volume. Okay, so right now we need to find a way to calculate the volume or area of the settlement, this place. So we assume that the area of this place equals to the area of a triangle. So we calculate the settlement area, use this equation. You can see it's like the area equation for triangle. We have the D, and then we have the height of the triangle here, which is SW, which is the settlement at the edge of the excavation. So we use this kind of simplification method to calculate the settlement area. Okay, so this one should be equal to VS, and then we can get SW, which is the settlement at the edge of the excavation. Okay, and here the next step, we compute remaining ground loose settlements, assuming a parabolic variation of S from D towards to the wall. So here you need to pay attention. So the 0 point of X is the same for the second method. So the 0 point of X is here. It's different from the first method, in which the 0 point is at the edge of the excavation. Okay. So here is the equation to calculate the settlement, the ground settlement from the edge of the excavation to this point where there's no settlement. Okay. And for the lateral deflection profile, as we talked about before, we prefer to use numerical methods. For example, here, we can use the so-called flu software to calculate the lateral deflection of the retaining wall. So right now here, you just need to know we can use different methods to calculate the deflection. So if we have any assignment, or if you find, if we have this kind of calculation in exam, so usually we will give you the deflection directly. So we will not ask you to calculate the deflection because it's too complicated for hand calculating. So don't worry about how to calculate the lateral deflection of the retaining wall, okay? You just need to understand how we can get the deflection, the lateral deflection, okay? So this is the first method. And then the second method is subgrade reaction method. And this method, I think you have already learned it in the lecture 3 for the pile foundation. For pile foundation, subjected to a horizontal load. So for this situation, if we have a soil here, we can also use the subgrade reaction method. So in which we assume the soil is a spring. So we have a spring, 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 spring. And the stiffness of the spring is calculated by this equation. It's the same as the one you learned in pile foundation. And E is the Young's modulus of the soil, and A is the distance between the middle point of element of two adjacent nodes. Okay, so L is the spring length. It's considered that this model is not realistic for most retaining walls. It's mainly because we have no assistant can be chosen here to determine the friction, the spring length. So this spring length will affect the spring stiffness. So it's easy to imagine. So different people may choose different lengths for calculation. So if we choose longer spring length, we will get a smaller K. So which means the soil is softer. If we choose a smaller L, we may get a larger stiffness, which means the soil is tend to be stiffer. So this is too subjective. That's why we don't recommend to use this method to determine the lateral deflection of the retaining wall. So here you can see this is the result from this software, Flu software. And this is the retaining wall. And here we have soil here. Here we have excavation. And then from the software, we can calculate the shear stress along the retaining wall. And then we can get the moment, the bending moment along the retaining wall. And most importantly, we can get the displacement or lateral deflection of the retaining wall. Okay. So far, do you have any questions about how to calculate the lateral displacement and the settlement of excavation? So if you have any question, you can also send me an email and I will explain it to you maybe in next week tutorial or latest lecture. Okay, let's continue. So now let's talk about the heave of the bottom of the cut-in clay. So actually this one, I think we don't have enough time to talk about this in today's lecture, because I also want to talk to you about the bearing capacity analysis. So maybe we can continue this after 2 weeks. And here I want to remind you, so next week we will have invited guest, Professor Philip Chong, which is the deputy head of geotechnical engineering office. So I hope all of you can join next week's lecture which will be given by Professor Philip Chong. And I think you will learn a lot of practical knowledge from Professor Philip Chong. And also you can have a brief idea about the current geotechnical development or civil engineering development situation in Hong Kong. Okay, so maybe we can stop our lecture here. If you have any question, you are welcome to send us email. Okay, so let's see you in next week's tutorial. Okay, so see you everyone.